Hello and welcome back. This lecture we're going to commence our study of quantum conformal field theory. In the previous lecture, we looked at conformal symmetry in the context of classical field theory. And we did that because we want to see what are the analogous properties and results that are going to carry over to this quantum setting that we're really interested in. And probably the most important observation from the previous lecture is that if you have a classical field and then you do a dilation on this field, a scaling transformation, then it transforms in a very particular way. And that was the main result of the previous lecture. And this particular transformation law for a classical field serves as a kind of basis for definitions in this quantum field case that we're going to move to for the rest of the course. So if you recall, if I can find it to make sure I use the same notation today, when you do a dilation on a classical field, then it is transformed something like this. Did I have a minus there last time? Okay, good. So if you do a dilation of space, then a classical field gets mapped to itself, multiplied by the scaling factor here, and this factor, or this number here, is the dimension or the scaling dimension of the field phi. And every different type of field has its own scaling dimension. Boson fields have d over 2, fermion fields, other dimensions, and so on. It depends on the dynamics that your classical field enjoy. So this is the core sort of notational observation, also structural observation, that we're going to carry over into the quantum setting, I mean, along with everything else we've observed. But this is this is a key piece of additional information that we learned in the previous lecture for classical field theories. But today we're not going to be doing classical fields anymore. We're only using them as a basis for generalization or for notation. In reality, the universe is quantum and always has been. And to that end, we need to start doing quantum theory, and we only ever use the classical limit to just check that our theories make sense. So the idea of today's lecture is not to quantize a field, but rather to say, suppose we have a quantum field, what are the constraints of conformal invariance on that theory? We're not going to build theories. We're just going to suppose that we have a theory. We have a quantum field theory. We've done all the hard work already, and we know it's conformally invariant, and so we just wonder, what are the constraints? Because when you add symmetries, that's the same as just adding constraints. So what are the consequences of these constraints on your favorite quantum field theory? Now, to talk about quantum field theory, we have to talk about quantum field theory. So we want to use it, be as, sort of as general as necessary without being too general. And so we have to somehow come up with a working definition of what is a quantum field theory. I think it's fair to say there isn't one yet, not a correct, universally agreed upon, mathematically rigorous definition of what is a quantum field theory. In 1 + 1 dimensions, we're getting close to one. There's 3 approaches. I'll just put bullet points here. I won't explore this in any details. So there's the approach via vertex operator algebras. This is all 1 + 1 dimension. There's an approach via and there's roughly sort of 3 approaches that are showing promise in 1 + 1 dimensions. So the first by something called vertex operator algebras. You take some structure that you notice and then you promote it to a fundamental mathematical structure, and then you try and build field theories from these things. Towards the end of this course, we may hear some seminars on vertex operator algebras. There's another approach via something called algebraic quantum field theory, where you work completely top-down rather than bottom-up, and you just look at, you attach to any space-time region an algebra of observables, and then you try and make sense of that as a field theory. And there's a third so-called functorial approach due to Graham Seagull, I guess, originally, where you look at functors from some n category to the category of Hilbert spaces. Now, each of these suggests some different kind of ways to define quantum field theory in higher dimensions, but for 1 + 1 dimensions, they're more or less close to equivalent. I'll put equivalent definitely in scare quotes here. They're not, these 3 formulations are not directly equivalent. But if you add some adjectives to each of these 3 formulations here, then you can show that the resulting mathematical structures are equivalent. This is still ongoing research. So these are the 3 sort of mathematical approaches you could take in 1 + 1 dimensions, and we're not going to follow really any of them. Instead, I guess the approach that we're going to take in this course will be closest to this vertex operator algebra approach. Instead, we're going to just give a laundry list of data that a quantum field theory ought to supply and then see what the consequences are of conformal symmetry. So, well, the first thing to note is that anything that you would call a quantum field theory, well, is got to be a quantum theory, right? So quantum field theory contains the word quantum. It's a quantum theory with extra stuff. So the set of quantum field theories is a subset of the set of all quantum theories. So that's the first assumption of this course. Seems like this seems like a trivial and a ridiculous observation, but there is a school of thought which says that quantum field theory shouldn't be defined as a quantum theory, but instead the path integral should be promoted to the first-class citizen, and that you define quantum field theories in terms of path integrals, which don't directly have an obvious interpretation as quantum theories. So if you want to follow that line of thought, then you're welcome to. But in this course, quantum field theories are quantum theories. Because they're quantum theories, I wouldn't go so far as to say that that comes from the Feynman school. I think it's fair to say there's a school of thought which says the path integral is the most fundamental object, and all things are derived from the path integral. And the path integral isn't directly a quantum theory, depending on how you implement it. Not directly. stuff to prove if you wanted to show that it's a quantum theory always. But this is really not stuff that's going to concern us in this course. Instead, we're just going to write down some data and then work out some stuff. So the data, well, we have a quantum field theory is a quantum theory. So what do quantum theories have? Well, they have a kinematical space, H, which is a Hilbert space. This describes all the states of the theory. So every quantum theory has associated to it a Hilbert space. Now there's going to be some interesting features of a quantum field theory as opposed to your favorite quantum theory. So usually the observables for a quantum theory are just, say, B of H, all the bounded operators on H. Here we will focus on a completely different set of observables, but I'll get to that in a minute. Now, we're talking about conformal field theory here. So we have to be able to talk about the symmetries of conformal group and the only way such things can be discussed is if you have some projective unitary representation of the group, the conformal group. So this is RPQ. So whatever a conformal field theory is, it's a quantum theory. It has to have the symmetries have to work on this quantum theory, so they have to be projective unitary operations by Wigner's theorem. Vacuum. So we're going to have something that we call a vacuum vector. There's a special vector in this Hilbert space, which we isolate and give us a name. We call it 0, the vacuum vector. And what we're going to demand is that this vacuum vector is invariant under global conformal symmetries. I mean, we might let it depend on a phase. So depending on the dimension, the global conformal group is a bit different to the local conformal group. So if the dimension P plus Q is bigger, strictly bigger than 2, then they coincide. The global group of conformal symmetries is the same as the conformal group. That's something we've observed in the previous lectures. However, when P is 1 and Q is 1, then the group of the conformal group becomes much bigger. It's this diffeomorphism group of the circle, and the global conformal group is a subgroup of that. And so all we're demanding is the vacuum vector is invariant under the global conformal transformations, but not necessarily the local ones. This is a crucial point. Which means that given the vacuum vector and the unitary representation, you can build the entire Hilbert space just by acting on it with the full conformal group. And now, well, we need to talk about what are we allowed to observe. So we have dynamics in the form of this unitary representation here. But what are we allowed to measure in this theory? It's not a complete theory of physics yet until we have the observables. And what we're going to say is that we're not going to allow all of B of H, or at least we're not going to demand that we predict the results of every measurement in the set of bounded operators on Hilbert space H. Instead, we're just going to demand that we can predict the outcomes of the measurements of local observables here, AX, or no, I wrote it differently in my notes, JX, where X is some space-time location, an event in space-time, and J is some additional label, that lives in some index set, J, big J. So we're going to assume we're going to have a whole bunch of observables, A, J, comma, X. So our observables are labeled by a type of particle, and that could be referring to bound states and all kinds of different particles, fermions, bosons, densities. This is just a generic label for all the kinds of things that you might want, all the different types of particles you might want to observe. And X is another label, a continuous label, which is events in space-time. So what this says is that the very minimum observables we demand that we're able to make predictions for and actually carry out experiments for are ones labeled by space-time locations X. And this forbids non-local observables, or at least we're not saying that we demand we can predict the results of non-local observables, like, I don't know. It's very difficult in a field theory to imagine a fully non-local observable, but you could, in gauge theory, the easiest example is a Wilson loop or a Wilson line. They're non-local observables because they are spread over a non-zero dimensional submanifold. And you could imagine even more crazy things if you want. Yep.
So far, the X is only a label of
the X A. Is only a label of the A's.
You didn't make any requirement of locality. You didn't say.
No, that's a good point, a good observation. So here I just said X is a label. I didn't say that this A is local in any sense yet. I just said that we have a bunch of observables labeled by this quantity X. What makes them local is commutation relations, causality. That's not actually, we don't actually write it down here. In a sense, this is induced by the next thing I'm going to write down. But strictly speaking, I haven't said that they're local yet. And what locality means has to do with causality, right? So I'll just make a comment about that. You know, these could be hugely extended objects. I mean, what makes them local is that if the invariant interval x minus y is space-like, then for all x, for all j x, a, k, y are jointly measurable. That's, I think, the most correct definition of locality that you can demand. So no matter if x and y are space-like separated, then you can always jointly measure the observables labeled by x and y for all x and y space-like and for all j and k and so on. This has the consequence in quantum theories of of ensuring that these things commute when it's space-like. I didn't say that they were Hermitian operators or anything like that. They're let's just make them self-adjoint operators. Self-adjoint. so that we can allow unbounded things as well as bounded things. Right. So that's the dynamics, the kinematics, the observables, and the Hilbert space, plus some dynamics given by this representation here. Let's now take a lesson from what we learned about classical representations of the conformal group and require even more. So we're going to introduce a certain subset of these observables called quasi-primaries. And a quasi-primary field is one of these local observables which transforms in a particular way under this conformal group. Quasi-primaries are local observables with additional properties. So there's a subset of all these local observables aj, x. Denoted, we give it a name or a notation. Phi hat A, no, I use K. So every one of these things is one of these things, but not the other way around. So we suppose that there's a special subset such that, why is it special? Well, it's special because if you do a conformal transformation, then these things transform in a very particular way. Under dilate. So x prime is just g of x, and g is a conformal transformation. Oh, there's a k missing. Yep.
Did you switch the notation or shouldn't there be a minus in this?
Did I switch the notation?
The last lecture
Did I have a minus up there in the last lecture? Okay. I will check. All right, I didn't. Yes, it's true. In the previous lecture, I did have a minus sign there. So we'll just do everything, we'll redefine everything so that there's a plus symbol there from now on. Now that one missed, I missed that one. Yeah, I used multiple references to prepare these notes, and that one I missed. All right, so when you do a conformal transformation on one of these so-called quasi-primary fields, then it transforms in this very particular way like this. Now, at this point, that's just all we've done is just made an assumption, right? So the whole story goes like this. Suppose that we already have a Hilbert space, a projective unitary representation of the conformal group. Suppose that we have a special vector called the vacuum vector that's invariant under this transformation. Suppose that we've got some local observables. And suppose that further, some of those local observables have this very amazing property like that. Then consequences. And that's what the structure of today's lecture is going to be. We're just going to look at what's the consequences of these assumptions. But at this moment, you should be thinking, well, are there any such things? Maybe this is, you can prove amazing things if you make amazing assumptions. It's tremendous. But often the only things that obey your assumptions are like the number 0 or something like this. So you have to be careful to show that this is non-empty, that there exist examples for these things. Does there exist a non-trivial example of a field theory which exhibits all this stuff, which has all that? The answer is yes, right? I mean, this set of things that obey those criteria there is non-empty set. And the classical examples are the free boson and the free fermion. So the massless boson doesn't directly fulfill these requirements, but if you take a certain subset of observables of these phi hats, then you do get that it obeys these requirements there. Similarly, the free fermion has these properties as well. Hopefully we'll get to see this in this lecture, in coming lectures. So there exist non-trivial examples. So there is a point to what we're doing. In fact, there exists a lot more non-trivial examples than just the free boson and the free fermion. Okay, but that's not what we want to do today. We're not constructing field theories. That's the hard part. That's the microscopics. Constructing field theories is, if you like, the hardest part of doing quantum field theory. Finding consequences of axioms and assumptions is the easy part. So let's do the easy part first. Well, the main consequence of these assumptions here is a statement about how correlation functions transform. This is a 0 ket, the vacuum vector. So under a conformal transformation, you just refer over to this rule over here, and you already know how this thing's going to transform. This endpoint function is going to have a very particular form. I know it is the same as the previous lecture. Sorry, this has been bugging me the whole time I've been writing this. Referring back to your question, isn't there a difference in minus signs here? There actually isn't, because in the previous lecture I had the prime here, but in this lecture I'm putting the prime over here. Okay. So actually it is the same. Good, I'm glad. That was a good question. So this, how does the things transform? Well, in the new transformed field operators, go like this. So this is just straightforwardly substituting that rule into that vacuum expectation value. But now I have the primes in the wrong place again. Hang on. So last lecture we had no, that's consistent with the last lecture. Yeah, with the pluses, yeah.
This equation isn't right then, alright?
One of the two isn't right, yeah.
I think you have to put there the primes, and that's everything right.
Ah, yeah, the prime's there, yeah? Yeah, now everything's right. Sorry about this confusion. Yeah. Good. So this is the fundamental consequence of conformal symmetry if you have a quantum field theory that obeys all these assumptions over here. And there's a reason why we focus on these things. We like them because these correspond, they're not directly quantities you can measure, but they're just about measurable in scattering experiments. And so they're called endpoint functions, or they have various other names, green functions. And so we focus on these quantities because they're the ones we can observe. And also, there's a converse theorem. If you know all these quantities for all field operators phi and all positions xn, then you can often reconstruct a quantum field theory just from that data. So this equation star constrains possible two-point functions, or endpoint functions. Not any old function can be an endpoint function of a conformal quantum field theory. And to understand this better, understand what that functional dependence on x1 through to xn actually can be for a conformal field theory, we're going to look at the invariance of the conformal group, just acting on space-time. What quantities are left invariant by the conformal group. Because these must be functions of those invariants. Now note that this is only assumed to be true for global conformal transformations. I didn't say that explicitly. But and the reason that is that the vacuum, see how the vacuum here and here, that can only work if the vacuum is invariant, this equation. And that's only assumed to be true for global conformal transformations. If you do local ones, then all bets are off. Something more complicated happens. We'll investigate that in the next lecture. Okay, so we just look in turn at each of the different kinds of conformal transformation you can do and ask what's left invariant by it. So here's translations. What quantities are invariant under translations? Well, x, a single location x is not left invariant by translations. But if you have xj and xk, two locations in space-time, then their differences are left invariant under translations. So instead of there being d independent variables, we've cut down the number of independent variables we have already. So instead of there being d squared such quantities, there's only d n minus 1 such quantities. Now if you have a spinless object, there's no non-trivial rotation dependence, then it can only, well, there's also a problem if your space-time dimension is too small. But let's assume that we're looking in sort of a sufficiently large space-time dimension. Then invariant quantities sorry. So this n refers to the number of these different choices here. So j runs from n. J goes from 1 to n. It's the same n as over here. Yeah, but I used a big N here. Okay. So actually, the constraint of rotation invariance is a rather huge constraint, because it says not only can your quantities no longer depend on absolute positions, they can't even depend on differences anymore. They can only depend on lengths, right? Because if something's rotation invariant, then it can't depend on the angle, it can only depend on the length. So we're left with n choose two such quantities here that an invariant quantity can depend on. But wait, there's still more. we're not done with all the possible conformal transformations. The conformal group is generated by two other kinds, namely dilations and special conformal transformations, and we have to see what's the consequences of invariance under those quantities. And the next one, dilations, is also highly constraining. So RJK is not invariant under a dilation. If you take x to lambda x, then RJK goes to lambda RJK. Well, that's bad. It's not invariant. Can't depend on the lengths then. We can only depend on the ratios of lengths. That's invariant. If you change scale, then all these lengths change as well, but their ratios don't. So under xj goes to lambda xj, RJK is not invariant, but RJK divided by RLM is invariant. Well, that's not everything still. Special conformal transformations. Don't leave these quantities invariant. So under a special conformal transformation, we have that the length of a difference squared is the length of the original difference divided by some horrible quantity. So these ratios here transform in a nasty way under these special conformal transformations. And in fact, the only things that are left invariant, this is a exercise. The only things that are left invariant are, well, products of these ratios, but very specific ones, namely so-called cross ratios. So So when you do a special conformal transformation, you pick up these factors, one per j, k, l, and m, and you need that they cancel, and that means j, k, l, and m must appear also in the denominator as well as in the numerator. And further, we must have that our quantities are functions of these ratios. So the only way you can get that to work together is to have things to be functions of these cross ratios. So these are the invariants of the conformal group. Under the full conformal group, these quantities don't change. So our correlation functions, which also are invariant in this particular sense here, must be somehow functions of these cross ratios. That's the consequence here. Because we're not doing anything quantum anymore. What we've got here is a many variable function, g1 of x1 through to xn, which is invariant under a very particular sense. And some normal many variable function that's invariant under a group of symmetries has to be a function of this reduced set of parameters here. We're just spending the symmetries that the group gives us. So actually all these assumptions were a way of getting quantum mechanics completely out of the story and rendering us, or bringing us back to the land of many variable functions. And this is where the interesting stuff begins. Now we're really going to do some physics in earnest. Because if something is a conformal field theory or close to one, then you've got your theory, you've done some work, you've tried to solve your theory. Maybe it's some sort of lattice model approximation, maybe it's some other field theory that you know how to solve. And as you've worked very hard, you'll eventually end up making predictions for these endpoint functions here. And then you ask the question, is my theory a conformal field theory, or is it sort of close to one? And then you say, well, if it's close to one, then it ought to be close to one. So the correlation functions have to be essentially invariant under all these conformal transformations. What do these correlation functions, what do they have to look like? And if you plot your correlation functions that you've worked out using Monte Carlo or whatever methods, and you see that they don't obey such transformation laws, then you already can conclude that your theory, whatever it was, isn't a conformal field theory or close to one. So this gives a whole bunch of criteria, necessary criteria for a theory that you have to be conformal. And this is how quantum statistical and classical statistical mechanics sort of works by and large. You plot by whatever method you can, you get endpoint functions, you plot them, and then you examine their behavior, and you say, oh look, this is very close to what a conformal field theory would have, or it's very far. Let's see what are the constraints in the case of our simplest non-trivial correlation function, namely a two-point function. We'll see it's already dramatically constraining. So star tells us, so star is this fundamental law here that we have by assumption. It tells us that the following correlation function, well, this is the behavior. I'm going to drop the k. We just assume we relabel things so that k subscript 1 is just the label 1 and k subscript 2 is just the label 2, just by relabeling. And I'm just going to drop the 0. I mean, all expectation values are with respect to the vacuum, so there's no point in putting the 0 in here. Now, let's start exploiting the symmetries that we know. So, the first symmetry that we know any self-respecting conformal field theory would have is translation invariance. So translation invariance immediately tells you that the left-hand side, so the Jacobian for a translation is nothing, is 1. So translation invariance tells you that this thing here can only depend on the differences of x1 and x2. And furthermore, why don't we just use the fact that it's rotation invariant as well? The Jacobian of a rotation is also 1, so the left-hand side and the right-hand side are equal. And then you can see that the left-hand side can really only depend on the length of the difference. Indices and primes. Have I missed indices and primes? Oh, on the x's, for example. I've missed indices and primes, yes. No, the primes and the phi I haven't missed. So, oh, yeah. Well, this is a true statement, but I should have done that. So this is the prime is what happens when you conjugate with the unitary. So it's probably less confusing if I have no primes here. All right, so this g x1 of x2 isn't really a function of just is an arbitrary function of x1 and x2. It can only be a function of this number here, the separation between x1 and x2. Some function of R1, 2. There's one single number. Now under dilations, we know that the left-hand side is the left-hand side, but the right-hand side is something different. So whatever function f is, it has this nice property that if you rescale its argument and multiply by lambda to the delta 1 plus delta 2, you get back the function. And you can start to experiment with what kinds of functions have that property. Check, does the number 1, like, just do some examples. Does the function f of r1, 2 equals just the number 1? Does it have that property? The answer is no. So it can't be that. What about the function f of r is r? Well, no, that also doesn't have that property. In fact, there's only one particular function that has that property. The way to work it out is something like this. So we do some series expansion for our function f of a, f. So it might be that f can depend continuously on this label a, in which case we have to do an integral over this index a. But for the very first check, let's just assume f is some series in R1, 2. And you ask, what can these coefficients fa be? Well, the answer is it has to be 0. Unless A happens to equal exactly minus delta 1 minus delta 2. So the only function that obeys this, has that particular property there, is a power law. Some single constant that you need to know. So this single constant, can depend on the two fields, but is determined by the normalizations of those two fields. So it's pretty amazing, right? You started off with a general quantum field theory, and then just by imposing translation, rotation, and dilation invariants, you already know that your correlation functions have to be power laws. So if you see anything that's not a power law in your system, it's already not conformally invariant. Actually, there's more. We have one set of transformations we haven't used yet, and those are the special conformal transformations. So it's a little exercise. If you do a special conformal transformation, not even these functions are already too general. In fact, the only solutions are when the scaling dimensions of the fields themselves are equal. Otherwise, you get 0. So if you solve your system and you find that you have two fields, perhaps with differing scale dimensions, and then you compute their two-point correlation function and you get something that's not 0, if these two dimensions are different, then you know it's not conformally invariant. Well, at least it's not invariant under the full global conformal group. It's invariant under the subgroup generated by translations, rotations, and dilations. And that's the full story for the two-point functions. So let's do the whole thing again for the three-point functions. So under dilations, rotations, and translations, you quickly just do exactly what we did before. And you quickly conclude that whatever that correlation function is, it can only have that kind of functional dependence there. Where these triples, A, B, and C, that you're summing over, have to equal delta 1, delta 2, delta 3. So here you're summing over 3 variables, independent variables A, B, and C, subject to one constraint. So there's actually some freedom here. These functions could be a bit more general. However, when you calculate the consequences of special conformal transformations, you again very heavily constrain the outcome. See what we get. Well, it's an exercise, but I'll give you the summary. It's not that difficult to convince yourself that under special conformal transformations, the only functional dependence that these triples can have is the following. A must equal delta 1 plus delta 2 minus delta 3. B must equal delta 2 plus delta 3 minus delta 1. And C must equal delta 3 plus delta 1 minus delta 2. Yep. And that implies that the 3-point functions aren't really functions of arbitrary triples subject to a constraint, but in fact, they're again a function of only one constant, and the rest is determined. All right, at this moment, you might be starting to think conformal field theories might be very trivial indeed. I mean, so the 0-point functions are trivial. The 1-point functions you can just set to 0 by a shift. The 2-point functions are a function just of one constant. The 3-point functions are a function of just one constant. Maybe, just maybe, conformal field theories are just super trivial. Well, the answer is they're not, actually. This is where all the simplicity stops, because for 4-point functions and above, we don't have enough invariance to completely determine them. So I'll write out just the general answer for n is 4, and it just gets progressively worse. Turns out that the general 4-point function is a function of the 2 cross ratios . So these are independent quantities. And some product of these RJKs. where I'll just put dots in here, and delta is the sum of these scaling dimensions like that. So there's no constraint on what this f looks like. It's just an arbitrary two-variable function. But once you know it, then everything else is completely determined.
What's the index on the last delta?
Delta, that's not an index, that's delta divided by 3. So this is for arbitrary space-time dimension. For d equals p plus q is anything. So everything we said is true for all space-time dimensions. For d is bigger than 2, strictly bigger than 2. So now let's investigate the somewhat more special case of d is 2, the one that really does interest us in this course, and see to what extent these results are also true there. So the reason d has to be bigger than 2 is that the comment about rotation invariance doesn't work in lower dimensions. Two dimensions. In 2 dimensions, we're going to slightly adjust our definition of what is a conformal field theory, quantum field theory. In particular, we're going to focus our discussion here on the case 2 plus 0, so Euclidean space. So in this particular case, we defined some complex variables z, and we introduced this independent z bar. So what's happening here is that, well, firstly, we've done nothing. We just changed variables. But now we're assuming that we have observables that depend on space-time location. Our observables, our things, our quasi-primary fields, we're going to assume that they're labeled by space-time location. Well, obviously, under a change of variables, you could just say that they depend on z and z bar instead. You know, once you've given z and z bar, then you know exactly what x1 and x2 are. So that's just a trivial relabeling. But we're going to make a big assumption, namely that these things also make sense for z and z bar independent. We somehow know that they make sense. That means, and the words we're going to do is we're going to assume that they can analytically continue the dependence of the field away from z plus z bar is real to the case where these are independent. So we're going to assume from now on that z and z bar are independent complex variables, and that this thing here on the also makes sense for that case as well. You don't have to make that assumption, but if you don't make that assumption, then life is more complicated. So, and it turns out that many of the theories we know and love have that, or can be made consistent with that assumption. So we're going to extend what we mean by quasi-primary as a consequence. And I'm going to throw out the word quasi and call it primary of type h, h bar. I'm going to introduce a special class of fields that are transformed in a very particular way under conformal transformations. This is by analogy. By analogy with the general case, we're going to introduce special fields that under a conformal transformation transform just like that law up there, but with a slight modification. Because remember that a conformal transformation, or a local conformal transformation, sorry, is an analytic function f in 2 dimensions. Oh, yeah, I didn't finish writing the exponents. This is an h and h bar. This is a definition. Just by analogy with the general case,
What's that prime? You didn't use it.
I didn't use it. Yeah, right. I could have just put z primes in here, but I didn't. I chose not to. All right, so this is of type or conformal weight. So if you have a field, if you have observables labeled by these z's and z bars, and under this particular transformation, z goes to f of z, where f is analytic, that field happens to transform like that, then you're going to go ahead and call that primary field of conformal weight h, h bar. This is largely by analogy with the quasi-primary case in the arbitrary dimensions, but it obviously has a little bit more structure to it because it's imposing how it transforms under analytic functions now instead of just conformal transforms. And we're going to just do exactly what we did in the general case for these special operators like this. And it turns out that conformal field theories have primary fields. It's just we can present examples where these equations are obeyed. Of course, there exist field theories where such operators don't transform in exactly that way. About those, we can say less. But it turns out enough interesting physical theories exhibit primary fields like this that it's worth doing this. So to proceed, it's actually more convenient to work with infinitesimal transformations rather than full global ones. So we just have to work out the infinitesimal version of this transformation law here. So infinitesimally, what does this transformation law look like? So the difference between the left-hand side and the right-hand side for an infinitesimal transformation is such, or so. So it's just a straight up matter of expanding the right-hand side to order epsilon and taking the difference between the left-hand side and the right-hand side. D is d dz. Epsilon is epsilon here. Where? We did 2-point functions. The question is, did we already do 2-point functions? We did when the space-time dimension was bigger than 2. We haven't covered the case where the space-time dimension is 2 yet. And the reason that we only did much bigger than 2 was that our result that rotation invariance means that our functions can only depend on lengths isn't valid in low space-time dimensions. So we actually haven't completely analyzed this case yet, although we have a good sense of what's going to come up. So we have this transformation law for these field operators. And now we're going to apply that. Yeah, question?
Yeah, I'm not sure why we can say that these Z transform like they only depend on Z and not on Z bar.
This line here?
No, this under. Because we say these epsilon only depends on Z, but we say that Z bar is independent of Z. Why doesn't it depend on Z bar?
So this does depend on Z bar, here and here.
Yeah, of course, but...
Oh, I just didn't write out the... Sorry.
No, that's clear, but why can we say that it only depends?
Oh, why can I say that this only depends on Z and Z bar? It's an assumption. Yeah. So it might depend on Z and Z bar. It might not be independent, have an independent dependence on Z and Z bar. Yeah, such theories exist, right? But here we're assuming that, oh, well, let's posit further that the dependence is, in fact, you can extend it analytically to Z being independently on Z and Z bar. And what are the consequences then? And it turns out enough interesting physical theories allow you to do that. As we'll see, it's got to do with whether or not you can analytically continue the endpoint functions away from the real submanifold. So these things are only defined in a physical theory for Z plus Z bar is real. That's all we can say in a physical theory. But if this is like some function of Z and Z bar, like sine or cos or x or something like that, then you can often analytically extend a function beyond its domain of definition. So you can say, oh, well, if I just allow it to depend arbitrarily on Z and Z bar, then I still have a well-defined many variable complex function. Why don't I just go ahead and do that and see, do I get something sensible out? And the answer is you often do get something sensible out from making that additional, quite serious assumption. And we get a subset of conformally invariant field theories which have analytically extendable endpoint functions. We can understand what's the consequences of these assumptions on the structure of these 2-point functions and endpoint functions, and we'll get some answer. And then we have to show that the set of such theories is non-empty, and it just is. So let's go ahead and start working out the consequences of this very strong assumption here. So if our theory is invariant under some transformations, then the difference in the Green's functions, or the endpoint functions, has to be 0 under a symmetry transformation. And now we're just going to go in a case-by-case basis through the global conformal group in 2 dimensions. So here's the simplest case, where epsilon of Z is just epsilon. And then that tells us that G2 depends on differences. Then let's do rotations. Then it can only depend on absolute values. Well, not quite. We've analytically extended, so it doesn't quite tell us that it depends only on absolute values. It in fact tells us that we have to depend on z and z bar in a particular way.
By the C, you mean what complex conjugate?
By the
1, 2?
oh, here.
Yes. And C.
Oh, etc. Sorry.
You mean the sum to the bar?
Yeah, the same with the bars. Yeah, I don't want to write out the bars all the time.
Does these data operator act on the product of phi1 and phi2, or does it act only on one of the function like the Leibniz rule?
It's doing does the delta operator act on just one, or it's acting via the Leibniz rule here? Yeah. So this is all done to first order. That I didn't say. That's true. So let's say it's order 0 to order epsilon, right? Oh, okay. The global conformal group in 2 dimensions is translations, rotations, dilations are coming up next, and then special conformal transformations. So there'll be no surprises in the consequences of these symmetries. We're going to get out the same answers as the general case. Okay, that's the result of special conformal transformations right there. Oh, this includes dilations as well, these rotations. So things are sort of the same but a bit different as the last case. If H doesn't equal H bar, then this does exhibit some non-trivial dependence on Z and Z bar. But in the case that we have a so-called bosonic field, this is the definition right here, where H is equal to H bar, then our 2-point function has a familiar form. And similarly, I mean, this leaves open the possibility, of course, that H might not equal H bar. And then we have fields with spin. This would correspond to the case for fields of spin. We're going to avoid, we're not going to really consider that in this course. This is already a complicated enough set of theories when they do obey that extra constraint on their scaling dimensions. But you can go crazy and think about anything you want. We're not going to think about anything we want. Just focus on this quite constrained subset of theories. Now, the 3-point functions, I'll write them out and that'll be the last act for today. They also should look pretty familiar. So I guess I'll stop with that equation here.
And the C appears only one time.
The C appears only one time, yeah. I mean, I could have a constant here and here, but then I could just absorb them together into one overall constant. So the D equals 2 case, isn't actually any different to the D is general case, but the method of getting there is a bit different. So the summary is, in this lecture, we introduced something that a class of things we might call quantum field theories. Then we've analyzed what are the consequences of conformal invariance on the correlation functions of these theories. And then we've isolated sub-theories, subclasses of theories which have obey certain constraints. So for example, delta is H plus H bar is real, and so on. And then we've identified what are the possible correlation functions these theories could have. Note what I have not done today is present any examples. So at this point, it could still be vacuous. All of this could just collapse to nothing. There might be no physical examples of theories that exhibit these particular characteristics. There, of course, are examples, but it'll take us a while until we construct them. And that'll happen later in this course. All right, but for now, I think we'll stop there. Thank you.